Let's go part B. Okay, the first problem is called library books. So Beavertown Library only has a small pile of books. When a beaver wishes to borrow a book, they take the book that is on the top of the pile and records their name. When a beaver returns a book, they place the book on the top of the pile and record their name again. The problem gives you at the beginning of the pile what the distribution of books looks like, and they also give you the library records. So first of all, Alba borrowed it, then Felix borrowed it, Alba returned it, Marta borrowed it, Felix returned it, and finally Carto borrowed it. So what book did Cato borrow? So Cato is the last one here. This one really there's no way to most efficiently do the problem besides the fact that you have to go through one by one. So um let's title this 1, 2, 3, 4, 5, right? So when you have all of these, what you don't want to do is to keep writing these long names down for no point. So what you want to do is to convert them into numbers or letters or whatever to make it better for you um to realize the problem. So first of all, Albert borrowed. So he borrowed one, right? The top of the book. So this gives the 2, 3, 4, 5 remaining. Felix borrowed, he borrowed 2, and this gave 3, 4, 5. Albert returned, you see, he borrowed 1. So now it becomes 1, 3, 4, 5. Marta borrowed, so he borrowed 1. So it becomes 3, 4, 5. Felix, he returned. What did he borrow? He borrowed 2. You see that from the very top. So we have 2, 3, 4, 5. And finally, Cato borrowed. That means he borrowed from the top of the book. So we now go back to our code names again. So 2 corresponds to Curious George, and we're done the problem. So for this one, the main thing is to assign variables. When you don't assign variables, this question becomes a nightmare because you have to write all the names back like all again. So actually the property of like this like last book returned is the first book like borrowed like on top. This is encoding, this is called LIFO principle. So this is called last in, first out principle. So in computer science, like when you have like a collection, there's a certain principle called a stack. So it is one of the most fundamental theorems of like computer science, and this is something that you should look at. If you're into this, you should look into it. Okay, let's move on to the next problem. Okay, market exchange. A beaver goes to market to trade items. It has 1 carrot but needs 1 fir tree. Each stall of the market allows a different trade as shown. They give you all of these stalls. Basically, it's like what you give and what you can get out of each one. And the problem asks, which of the following sequences of stalls should the beaver visit in order to trade his carrot for 1 fir tree? What we want to do is to run through each answer choice and deduce the right answer. First one, after you pee, you get a fish, right? Right here. And then they run through Operation Q. Operation Q, you actually need to give a coin, but you don't have a coin, so this is eliminated. Again, like you only have one thing, so you really can't do much. Second of all, WTU. W gives a maple leaf, green maple leaf, but as you can see on the left, none of them actually requires a green maple leaf, or you can get so basically you can't get anything else after that. So we also eliminate B. SVU. Now what is S? Carrot, great. V, okay, so you get a muffin. V, you use the muffin to get a ring, right? You use a ring to get a tree, right? We found the right answer. So the correct answer is C, but we'll show why D is not a correct answer. SRU. S gives you muffin, but R uses a ring. So again, this is at the second point, it already false. So we can just eliminate the answer for the correct answer of C. Again, a pretty straightforward problem if you know what you're doing. So make sure, again, don't be fooled by this like big table. At this like stage, they will try to make it seem like very daunting. And the reality is that once you like decipher the problem, you have plenty of time in this contest, right? Because like you have plenty of time, so you should definitely use the time very well. So again, this thing like you can also do this in like a more computer science way. You can make a directed graph. So basically, it's like the vertices of the graph is like all of the objects, and then you use arrows to connect the processes. So for example, from a carrot, you can connect to three objects. One is the fish, right? In process P. One is the S, which is the muffin, and W, the maple leaf graph. So if you want to do that, sure, but it's going to cost you more time. But you can clearly see the process of how, for example, you go from one to another, really easily in your head. Okay, let's move on to the next question. This question is my favorite one out of my section because it is it's a it's one that needs more like elementary combinatorics and also um like slightly more advanced math knowledge. So get ready for this problem. To brighten up the street Main lives on, each white house will be painted red, green, or blue. Okay. Well, what about the ones already painted? Oh, they didn't say anything, so we don't change it. So we need to change the ones that are not painted right now, which is all of the white ones. So after all of the houses have been painted, the following must be true. Two houses next to each other must not be the same color, and the house must not be the color as the house directly across the street. And this is May's house. And the question asks, what colors can be used to get May's house? So this one is actually quite difficult. So I will take a slightly more time. So when you look at this problem, you immediately want to first look at the answer choices. Like how bad is this problem? Like how easy is this problem? Well, first of all, May's house is directly next to a red house, so why can't the only color be red? This already gives you elimination. So you already have a 1 out of 3 chance of guessing it correctly, even at the very end. So elimination is a key first step. Now we look at the conditions, right? So two houses next to each other must not be the same color. So let's consider this one. It must not be R. It must not be B. There's only 3 colors, so this one must be G. Okay, now let's consider this one. Again, you want to keep using the evidence that you already have to craft your problem. It cannot be G because it is the directly across one. It cannot be B because it's right next to it. So the only color that it can be is R, red. Okay, now we do this one, right? It um cannot be B and it cannot be R. Besides that, we only have green yet. Okay, great. Now let's look at this house. This house is neighbored by one blue and one green. Despite not knowing May's house, we already know that this one must be red, right? And finally, we can use this information to find May's house. May's house is next to a R, and a G. So the only one that we haven't used is a blue. Therefore, the answer is B. Yeah, so this question can be more complex when, for example, you're not given. For example, what happens if you're not given this one? So these questions could be, they could turn up, for example, like how many ways are there, how many arrangements of like house color paintings. This can actually really be an introductory like AMC 8, AMC 10, AMC 12 problem. So pay attention to it. This is like a more rudimentary case, but as you progress, these will become more harder. So this is combinatorics. And you can also use like graphs to do this, but at for this problem, it's actually quite straightforward. So I suggest you just try it out. Okay, next question. Yeah, I'm not a very big fan of this question, like this treasure hunt, but we'll get right into it. 3 explorers are working together to find a hidden treasure chest. They each take a different path, upper, middle, or lower, and they explore the path by going from left to right. There are 3 large obstacles blocking the path. Oh, several. Sorry, several. When an explorer encounters an obstacle, they must wait until it is crumbled before they can proceed. An obstacle is crumbled if only if when one of the explorers steps on a stone, yellow, that is marked with the same symbol as the obstacle. In fact, stepping on a stone crumbles all obstacles that are marked with the same symbol as the stone. The obstacles, stones, explorers are arranged just below. So essentially the yellow things, they are markers. So once you step on them, all the blockades just get down. So this is kind of like, like there's some video games that have these kind of stuff. It's like 2-player. So It's a very similar reasoning. Again, these problems like you don't need a lot of background, so just uh just deduce your way out one by one. Okay, now you see that first of all, like when you start running, only G has a chance of going forward, because this thing is in this these blockades are impeding anyone. So first of all, Gray steps on this and just takes these off, right? Now, uh, you see that all of the top two are stuck. So the bottom one steps on this tripod or whatever it's called, and deduces gets rid of this, and also the square. So they get rid of all the square ones for everyone else. Now the gray one is still stuck here, and the bottom one is stuck here. But the top one, all of their impediments are um are got rid of. So the answer is A. Like we see that although Gray has a head start, he gets eventually stuck at this point, which is the first point. He actually never passes through because there's no yellow button that has that mark. So the answer is A, where he just goes through. Okay. Oh yeah, by the way, just a quick extension. Like processing units. So this is kind of like processing units in parallel. So they can either work in series or in parallel. So in series is like, oh yeah, first this task goes and then the next task runs. But in parallel, it's like all the processors are working at this problem at once. So this problem is kind of like illustrating that in a more like metaphorical way. So all the tasks are like working together. And as opposed to inefficiency, where the first one must go to the end, then the second one. Um, so yeah. Okay, let's move on to the next question. Water bottle. It's more of an alcohol bottle. Danny is required to entirely fill as many empty water bottles as possible using a 50-liter tank. Suppose that she is given the following 10 empty bottles, where each bottle is labeled with the number of liters it can hold. What is maximum number of bottles that Danny can fill entirely? Oh yeah, so this question I just wanted to also do a slight extension. So like those like sock questions. For example, Ben has three types of socks. He has three gray socks, five red socks, and like six like green socks. And for example, at least how many must you take to like, it's like these optimization pressures. Like Ben must take like two of each and then add one to like ensure like a triplet, like so on and so on. This one, what you want to do again is to optimize. How do you optimize the maximum number of bottles? You use the bottles that have the least. Is this called the greedy algorithm? I've actually never heard of that. Okay, anyways, three. So we want to go from the least to the top, right? So we can range the bottles like 3, 4, 5, 6, 7, 8, 9, 9, 11. Uh, wait, where's the last one? Oh yes, 15. Okay, just make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait. Oh, there's two nines. Okay, so you want to fill up the maximum. So you take the 3, right? That's 3, and then add 4 is 7. 7 plus 5 is 12. 12 plus 6 is 18. 18 plus 7 is 25. 25 plus 8 is 33. 33 plus 9 is 42. 42 plus 9 is 51. So we can only fill the maximum this many, which is 1, 2, 3, 4, 5, 6, 7. The answer is B. I know that. Again, the last one, you run out of 1 liter, so you can't fill it entirely. This is the most trick point. The answer is B. Okay, I will pass it on to Friend to conclude this problem set.